Very good day, Doctor. We are from Group 2, Subgroup 1, presenting a journal reflection with title Enhancing Ethanol and Methane Production from Rice Straw by Pre-Treatment with Liquid Waste from Biogas Plant. World energy consumption is growing rapidly and supplying the demand from traditional energy sources is not sustainable. The utilization of non-renewable energy sources has resulted in greenhouse gas emission, leading to global warming and climate change. Among the various biofuels, biogas is a major green fuel, especially in rural areas.
Materials method. The raw materials that had been used in this study was rice straw. Pre-treatment of rice straw. The digested residue was centrifuged and supernatant was called biogas liquid waste. 16.2 grams of rice straw was mixed with 93 ml of liquid fraction of biogas digested in 150 ml reactors. These tubular reactors were placed in oil bath and heated for specified duration. Collected pre-treated materials were separated into liquid and solid phases by centrifugation. Enzymatic hydrolysis and stimulus saccharification and fermentation. Enzymatic hydrolysis was carried out in shaking flasks using 25 grams per liter solids in citrate buffer at pH 5. Cellulose enzyme was added into each flask and they were put in water bath. Straw samples were subjected to SSF processing for ethanol production. 50 grams per liter of substrate was added to 50 millimole per liter sodium citrate buffer containing fermentation nutrients. pH of all samples was adjusted to 5 using 2 molar sodium hydroxide solution. SSF process was conducted by placing the flask in a shaking bath at 37 degrees Celsius and 120 rpm for 48 hours. Liquid anaerobic digestion. 0.25 grams of each substrate was well mixed with a sufficient amount of inoculum to obtain substrate to inoculum ratio. Deionized water was then added to all samples to achieve 5% TS in each reactor. The reactors were sealed with beauty rubber and aluminum caps. Each glass bottle was purged with a mixture of 80% nitrogen and 20% carbon dioxide for 2 minutes to provide anaerobic conditions. Reactors were incubated at 37 degrees Celsius in an incubator for 30 days and manually shaken regularly during the digestion period.
For dry anaerobic digestion, DAD, an SI ratio of 1 and a total solid content of 21% was achieved by mixing 0.25 grams of treated and untreated straw. The materials were mixed well and then loaded into 118 ml glass reactor. Using similar procedures to the LAD setups, the blank reactors were set up to anaerobic conditions. The incubators were incubated at 37 degrees Celsius and were manually shaken regularly. For analytical methods, a constant weight was achieved by oven drying at 105 degrees Celsius to measure the total solids of substrate and inoculum. Measurement of the volatile solids content was done by placing the dried residues in a furnace at 575 degrees for 24 hours. Using the procedure from Adney and Baker, the enzyme activity was measured as 95 FPU per ml. HPLC was used to determine the contents of monomeric sugars liberated during acid hydrolysis. A lead 2-base column with 2 microgard Dishing cartridges, followed by microgard carbo P guard column, was used at 85 degrees Celsius using ultra-pure water at a flow rate of 0.6 ml per minute as eluent. The glucose and ethanol concentrations were also determined by HPLC using a hydrogen ion-based ion exchange column at 60 degrees Celsius with a microgard cation H-guard column and a 5 millimolar H2SO4 at 0.6 ml per minute as eluent. Nitrogen gas with a flow rate of 20 ml per minute at 60 degrees employed as carrier gas. The surface morphology changes after treatment were qualitatively studied by SEM analysis.
Result and discussion. Enzymatic hydrolysis of treated and untreated straw. Figure 1 shows the glucose yield of untreated and treated rice straw after 24 and 48 hours of enzymatic hydrolysis. This figure shows that increasing pretreatment temperature and prolonging pretreatment time shows higher yield of glucose. The highest glucose yield is 76% with sample pretreated with BLW at 190 degrees Celsius for 60 minutes. Figure 2 shows the ethanol yield of untreated and treated samples after 48 hours of simultaneous saccharification and fermentation. At pretreatment 190 degrees Celsius for 60 minutes using BLW, the maximum ethanol yield is 71%, while from raw straw is 32%.
Next is liquid anaerobic digestion. Figure 3.A shows cumulative methane production obtained in LAD assays between untreated and hot water treatment. Current studies show pretreatment with hot water was not successful, resulting in no increase in the methane yield. All samples treated with hot water had principally the same biomethane potential as the untreated one. Figure 3.B shows cumulative methane production obtained in LAD assays between untreated and biogas liquid waste or BLW. The straw treated with BLW showed a better performance during LAD assays. The highest methane production was achieved after pretreatment at 190 degree and for 30 minutes. However, increasing the pretreatment time from 30 to 60 minutes at 190 degree resulted in a decrease in the methane yield. This might be caused by inhibitory compound, which could have formed under the more severe pretreatment condition. Next is dry anaerobic digestion, or DAD. Pretreatment with weak acid caused leveling of degree of polymerization, which decreased in cellulose and crystallinity and degree of polymerization. Next is effect of treatment on the straw structure. Next, for FTIR analysis, calculated cellulose index shows that the treatment of untreated straw with BLW caused decreasing in cellulose index from 1.38 to 1.23 and 1.18. While for hot water treatment, it reduced to 1.23 and 1.24. Therefore, higher amount of cellulose 2 compared to cellulose 1 present in rice straw after pretreatment at this condition. Increasing pretreatment time at 190 degree led to a decrease in the methane yield. It was concluded that generally higher yield could be achieved in the LAD process than in the DAD process. Then, longer retention time was needed for DAD compared to LAD. DAD benefit is smaller reactor would be enough and better for an equal solid loading. For surface characterization SEM image, the results show raw straw with lower temperature give out image with crystalline and highly packed structure. For straw with more severe condition, it shows porous and penetrable structure.
3.5 Effect of pretreatment on straw. Table 2 shows the total solid TS and volatile solid VS contents of untreated and treated straw together with solid recovery at different conditions. There is no significant differences in the TS and VS contents of the sample. 3 shows chemical composition of treated and untreated straw. Result shows that at a temperature of 190 degrees Celsius, it resulted in an increase of glucose content and decrease in the silane content. Under the same conditions, treatment with hot water caused 80% removal of silane, while treatment with BW caused 10.6%. What is silane content? Silane content is an important factor in decreasing the accessibility of cellulose for enzymatic hydrolysis. However, it is not the only factor playing a role in biomass recalcitrance. This study shows higher remaining silane content after treatments with BLW. This will affect the glucose yield and ethanol yield in figure 1 and 2. This has contradicted the above statement that silane decreases the accessibility of cellulose for enzymatic hydrolysis. Hence, there are no strict relation between the hemicellulose content and glucose ethanol yields in this study. When pre-treatment medium changes, variation of biomass structure of the silane content occurs. The arrangement and location of silane biomass, especially the one surrounding the cellulose fibers, reduces the recalcitrant behavior of biomass also changes. For table 3, the treatment with hot water produces less acid-insoluble lignin AIL was presented in the straw compared to treatment with BLW. While there is no significant changes for acid-soluble lignin ASL after any pretreatment condition. It was concluded that better performance of straw samples pre-treated at higher temperatures in the enzymatic hydrolysis, SSF, LAD, and DAD could be related to the removal of hemicellulose.
In conclusion, the present study demonstrated the possibility of using a liquid part of biogas digested known as biogas liquid waste, such as the supernatant liquid phase obtained after centrifugation of digestion residue for the pretreatment of rice straw under different conditions. The results show that the enzymatic hydrolysis yield of untreated and treated straw increased from 38% to 76% respectively when the pretreatment with waste stream was performed at the best possible conditions, in which the production of ethanol was double-fold increased after the treatment. In addition, the highest improvement in methane production was observed after pre-treatment via liquid anaerobic digestion and dry anaerobic digestion, with scoring 24% and 36% respectively. So here are some reflections that we made throughout this study. As for benefits, agricultural residues such as rice straw have a huge potential for producing biogas. Next, pretreatment decreased cellulose crystallinity, increased accessible surface area, and decreased the lignin content depending on the mode of pretreatment methods functioning. Next, the use of pretreatment at high temperature favored the conversions of substrates to ethanol through the SSF procedure. Lastly, pretreatment increased the methane content in the anaerobic fermentation process. However, there are some limitations found in this study. First, hemicellulose acts as a physical barrier, preventing accessibility of hydrolytic enzyme and microorganisms to cellulose. Second, treatment with photo did not have a significant effects on the methane yield. And lastly, cost of operational, energy, and formations of inhibitory compounds. Therefore, here are some suggestions for future improvement. For maximum process efficiency, a very balanced and intelligent combination of pretreatment, hydrolysis, and fermentation process must be chosen. With the advance of genetically modified yeast, synthetic hydrolyzing enzyme, and other sophisticated technology, The process of producing bioethanol using rice straw will soon prove to be a feasible technology. On the other hand, various chemical, physical, and biological pretreatment have been used, the latter generating fewer inhibitory byproducts. To date, however, most of the proposed processes include more than one pretreatment to mineralize lignocellulosic biomass, increase the numbers of steps, and consequently increase the cost of biogas production.
That's all from us. Thank you.